Hello everyone, welcome back to the DSA for Beginner series. In our previous video, we saw what are arrays and how's the working of arrays, and we saw one example of how array behaves. Today we are going to learn our first searching algorithm. First is linear search and second is binary search. Linear search and binary search. Searching is one of the most common operations in software development. Whether you are searching for a contact in your phone, a product on Amazon, or a file on your computer, some form of searching algorithm is being used behind the scenes. By the end of this video, you'll understand how these algorithms work, when to use them, and their time complexity. Let's get started then. So, what is searching? Searching means finding whether a particular element exists in a collection of data. Let's suppose our array has 10, 25, 30, 45, and 60. Let's suppose we want 45. We need to search this particular element in this array. So, these two algorithms will let us know how to search this particular element in an efficient way. So the first simplest approach is linear search. So what is linear search? Linear search checks every element one by one until the target is found. So let's say here first 10 is taken. Is it equal to 45? No, not equal to 45. It goes to next element 25. Is it equal to 45? Not equal to 45. Again third one, is it equal to 45? Not equal to 45. Then fourth one, 45 is equal to 45. So then it returns the index of that particular element. So let's see how linear search is implemented in our Java code. So public static void main. Let's suppose we are taking an array of integers and then target. So let's take this as a linear search algorithm. So here we need to iterate through all the elements of the array and that length I plus plus. If a of I equal to target, then return I, or else return -1. So this is how. Let's see a simple walkthrough for this particular algorithm. So let's say, okay, so we need to change the return type of this because we are returning a index. So let's say first element comes up here, 10. It checks the same thing. Is it equal to 45? No. So it doesn't go here. So actually we need to return this outside the for loop. Second element comes in. So 25, is it equal to 45? No. Again, it goes back to next iteration. 30, is it equal to 45? Not equal to. Again, 45. Is it equal to 45? Yes. So it returns the index. So what is the index of this? 0, 1, So basically, what is the index of this? 10, 25, 30. Okay, so what is the index? 30 and 45. 0, 1, 2. Okay, so the index of 45 is 3. So it returns the index, which is 3. Okay, so what is the time complexity of linear search? So let's say my element is 10, the target is 10. So what is the time complexity is that the first element only we got the target. So the uh, time complexity will become O of 1. Let's suppose the target is 60. In that case, what would be the time complexity? So we need to iterate through all the elements. So it will become O of n if the target is 60. O of n if 60. So let's suppose we have 1 million records to search. Let's suppose the target is somewhere around 100k. So worst case complexity will become O of n, which is not accepted. So can we do better? That's where we have binary search. So what binary search does? So let's take an example of 10, 20, 30, 40, 50, 60, 70. So let's say we are searching for an element 50. How does it work? Instead of checking one by one, we jump directly to the middle. So we will find the middle element. So which is uh, we have 7 here. 7 by 2 is 3. So which is 0, 1, 2, 3, 4, 5, 6. Third element is 40. So we check the middle element. If the target is greater than the middle element, so we go through right. And if it is lesser than the element, so we go through left. Hence, we discard the half of the array depending on the target. In that way, we will search only these 3 elements, which is right to the middle of the element. So we can see that the element is reduced to half of the array. This way, the searching is much faster because every step removes half of the remaining elements. So let's suppose if the array size is 1000, we will reduce the first, once we do the comparison, we will reduce the array element to 500. And then second comparison, we will reduce the array size to 250. Then again to 125, and then it goes on. So only around 10 comparison we need to search for the array size of 1000. Only 10 comparisons we need. So that way we reduce the comparisons drastically. So this is incredibly efficient. So let's say, okay, so this is the code for binary search. So let's have a dry run for this algorithm. So let's say left is at 10, right is at 70. So we will loop through the array until left is less than or equal to right. So that means left goes beyond right. So first we'll calculate the middle, which is left, which is 0, plus right is around 6 minus 0 by 2, which is 3. Then we'll check if array of mid is equal to target, which is not. So then we'll check if array is less than target, then we'll go to left, and then if it is right, if it is greater than target, which is in our case, so we go to right. In this case, left will be moved here. So left will be moved here, which is 50, left and right. Again, second time, we'll calculate the middle one, first iteration. Second iteration, left is 4 plus 6 minus 4 by 2. That is equivalent to 5. The mid value is this. Second iteration. Again, we'll check. If array of mid is less than target, then right will come here. So again, so right will move left. In this case, this is the right. So third iteration, what is the left mid calculation? Let's say right is 5 minus 4 by 2, which is 4. This is equivalent to 4. So A of mid is equal to target. Now we return. What is the index of the mid? Which is 5. Oh, sorry, this is 5. Sorry, yeah, this calculation was correct. This is 4. So the index will be 4, and then that will be returned. So what is the time complexity for this? Let's say we find the element in the first go. In our case, let's say it was 10, 20, 30, 40, 50, 60, 70. If the target was 40, in the first go only, we would have got this element. In that case, the complexity would have become O of n. Having said that, if it is not in the first go, so we'll keep dividing the array element size by half. In that way, so the worst case complexity of this will become O of log of n. Complexity of binary search will become O of log of n, because we are dividing the array elements into half. Space complexity is O of 1 because we are not using any extra space. So now let's have a comparison between linear search and binary search. So one thing we need to see in binary search is, so the whatever the list we are getting, right, so that has to be sorted. But in linear search, it is not needed. What is the worst case complexity? So O of n. So here O of log of n. Is it easy to implement? Yes, it is easy to implement. Binary search, not so much. So it is not very easy to implement, but it is not so complex to also. So moderate implementation. And which one is efficient? Linear search is not so efficient. Binary search is yes. So how do you decide when to go for what? So if the list says it is sorted array, then straight away go to binary search. Okay, so let's conclude today's lecture. Today we learned two important search algorithms. Linear search, which is simple and works on any array. Binary search, which is much faster but requires the array to be sorted. Understanding binary search is extremely important because it appears in coding interviews at companies like Google, Amazon, Microsoft, Flipkart, and many others. In our next video, we'll learn one of the most important techniques in DSA, which is two-pointer technique, a pattern which is used to solve array and string problems efficiently. See you on day 3, sorry. Happy coding.